Good morning, yes, sir. I'm Naavind from FTKE Unimap. My matric card number is 2112911019. So, today my name is Naavind. So, today I would like to present about my lab 2, that is dynamic response of second order system in control system technology. So, as I mentioned, these are the details about myself. Okay, so today I would like to explain about the dynamic response of the second order system. So for the section A, derive the transfer functions of the capacity of V out or Vs for the electrical network shown in figure below. So these are the circuit. By applying the transfer functions in the section A1 and the step functions as input, plot the response for the system by using simulating model and verify your answer by using the M file or commands window. So by referring the answer into a comment about the response of them. So from start beginning. So for the section B, consider the following second order closed loop system. So these are the questions. So once by using the simulating model, obtain the response for the each second order system A, B, C, D and verify the answer in section B using the M file or command window. Next, obtained by plot locations of the root of the system using M file command window. So comment on the response type of the each second order system, just this definition. So for the first part, so I done the calculation. So these are the calculations. So ut is equal to 1 over s. So I just substitute in the r and then the inductance and the so on. So we'll get the answer like this. So s equals to 0.1 s square plus 2s plus 50. So I just substitute into the circuit. So this is the step, transfer function and the scope. So for the answer, there will be some step and to be steady state after few seconds. 0.0, it's like 0.8 something or 0.6 to get a steady state. Before that got step. So for the second question, the numerator is 1 and then the then is 0.1, 2 and 50. So we'll get for the transfer function for the numerator and denominator the step G. So for the value here is 2 will get the same wave, but if we want the steady state, it's nearly 0.45 will get the steady state. So I already explained here, it is an underdamped graph response because of the graph shape, and he respond the rate by the transfer function of 0.1 s over 0.1 s plus 2s plus 50. So it's a symmetrical since the value of the input poles are origin. As the result, the underdamped quality of the poles zeros map may be seen clearly. So at the same time, instant conclude, I can see that the response is underdamped based on the graph output since its oscillator inside is falling envelope before reaching the steady state. So the second question for section B. So step function, transfer function and scope. So this one they already give on the top. So the steady state will be given by 2.8 or 2.7 to get to reach the steady state rate. So for the 16 over 2s plus 16, there will be no steady state here. If more than that, you can see how it result as. For the 16, s square plus 5s plus 16. These are the steady state value from 2 onwards. Before that got some discrepancy. So this one is the steady state after 1.6. So for this one, the coding, the result will be like this. The stop response will be more than 2, and the amplitude is from 0 to 0.9. But here, at least this one will reach the steady state at 2. But for this one, noise is still quite a lot, so the result will be like this. And this one also the same, will be steady state at 0.2. Then this result will be at 1.5. So these are the points. You can see here clearly. Okay, so for this question, they have a negative 4 pole. They have 4 pole damping, negative 4 poles because it's in the left hand side. And then its damping is 1 and the frequency is 4. So because of this denominator, your numerator and denominator, same time here will be on this side, on the top, the imaginary and on the top of this question. One save at 3. Then this one is 4 from the axis x. This will be get 4, negative 4, and then for the y-axis it is the near 0. So I will explain about here. So the transfer function is s square plus 8s plus 16. The value of the input poles at the origin occur at s equals to negative 0. I already mentioned about that. And the 0 does not exist, and the response of output is critical damp of the transfer function. Critical damp response are the faster response possible without an overshoot that is characteristic of the underdamped response. For this one, it is a underdamped. So underdamped is result of this characteristic. Understand underdamped response in input poles at original grade that the constant force response. The response called underdamped because this one is zeros does not exist, and the output for the transfer function B is underdamped, as I mentioned about that. Okay, for the third question, because of the denominator for the transfer function is 2s square plus 5s plus 16, the input is origin at axis S1 equals to negative 22.5 plus 3.12j, and S2 is negative 2.5 and negative 3.12. So 0 does not exist, and response output for the transfer function is underdamped based on the quantities. So for the fourth question, because the denominator is a transfer function s square plus 9 plus 20, so it is a overdamped. So it means the value of input poles at origin exists at S1 equals to 4, negative 4, and S2 is negative 5. So an overdamped is derived from the feature overdamped response. The input generates constant force response. Each the two system poles on the rear axis greater and exponential natural response. So this one also, it seems like a pole could be there from the response without creation calculation on the inverse Laplace transform. For discussion, what I learned from here is uh, student can beat out uh, from section A that the results of the transfer functions is the value and that the response obtained from the transfer is so there is a response obtained. The transfer function is underdamped because first of the value input pulled at the original. So the denominator of the transfer function and the zero exists at the original. So students can see from the graph output that the transfer function rise time starts at 0. So 0.0553, and then for the peaking at 0.257 before the stability at 0.429 seconds. So aside of that, section B as the for second order transfer function must be described in terms of response characteristic. Okay, so for that, because the denominator of a transfer function for A, the value of the input poles at the origin exists at s equals to -4 and 0 does not exist. And for 2A equation, the function is a critical damp. For the 2A and 3A are definitely of a critical damp response because the denominator of this transfer function is s square plus 16. Then for the B, it is underdamped. Furthermore, the figure post 0 maps at 3B shows that the further underdamped response. So from here, in figure C, one of these traits is underdamped and shown in figure 3C because the denominator of the transfer function is the response output for the transfer function is overdamped. So for the D is confirmly this overdamped. So conclusion. So what I learned from here is how to use a Simulink and Empire model in the MATLAB to characterize the dynamic response of the second order system, such as overdamped, underdamped, uh, undamped, and severely damped. So in this second lab, I will learn about how to simulate the transfer function by using the Empire or other command windows in MATLAB. As we the distinct between the two, the transfer functions can be created and writing some code in the Empire or command window and there obtain the desired output. So from here, this differentiation between two methods is that one, the output response is received. So we can see the rising time, peaking amplitude, setting time, and the steady state for the graph from the Simulink. Finally, the lab is completed and the objective will be achieved. Thank you, Doctor.